the reasons why APIs are important is because APIs encapsulate semantics. Well, when I give you an API, essentially I'm giving you a semantics that you can use in order to interact with that data. And this goes back to the second programming language class you ever had, where they introduced data structures and then talked about methods and why you should use methods rather than letting people go directly to data structures. It's the same idea, it's just on the web. Right? So on top of this architecture that we built to help us manage complexity, one of the things we do is we build semantics in the form of APIs, for example. But it turns out this is still hard. And the reason this is still hard is because there's lots of APIs. Successful applications are going to use a lot of different APIs. And so you have to understand the semantics of each of these different APIs. You have to tie them together. They all use a slightly different way of doing authorization, which anybody who's tried to use OAuth between 3 different websites knows, right? That even though it's a standard, it's just a little bit different on every one. And we have actually tackled problems similar to this before, problems of similar complexity. Here's an example. If you recognize that, it's like Intel assembly language, yeah, the older people in the room. What this does is it compares a number to make sure it's within a certain range and then subtracts if it is. Right? And you can read through it and we could work it all out. Turns out that's pretty hard to understand. What's more, doesn't do anything, doesn't tell you anything about variable scoping. Right? If we wanted scoping, we'd have to create a stack and push things on the stack and all of those complexities. Doesn't do anything about optimization. Obviously, this is a pretty simple thing, but more complicated functions need to be optimized. And it's not machine independent, obviously. That depends on a very specific processor in order to run. So how did we solve this problem? Well, we did this. We created notations, which then we can turn into the particular machine language that we want. So this notation is not any particular language. It's kind of C-like, but it essentially does the function that was in that assembly language. So now if you think about this scenario that I expressed before, managing all of the pieces of this is kind of like all of that assembly language. Right? Yeah, we can put it all together, and there's lots of pieces, and we have all the tools we need in order to do that, but there's a lot of moving parts, and it's pretty complex. So I'm going to talk to you about a way that I believe we can help solve this problem. So a scenario like that one in Borders could be described as expressions over events. So we could have an expression that looks something like this, for example. When the wish list changes before the user is in Borders, then do something. And what I'm proposing is that on top of this stack, we layer notation. I'm proposing that programming languages ought to do more to help us with this problem, rather than just giving us libraries and a bunch of what, on the web, amounts to primitive glue for putting it all together. Now, since 1993, when CGI arrived, we've been building a lot of applications online. And we've used a lot of different web programming patterns in order to do that. Most of them have been ad hoc, and all you have to do is look at a selection of CGI programs to see that there are a lot of different ways that people have come up with for managing this web app programming problem. Now, I think that one of the best ways to think about these kind of programs is as reactive systems. Essentially, what they're doing is reacting to events. Jeff Lindsay, who spoke in the last session, talked about webhooks, right, and the event-driven web. Essentially, everything looks like an event to a web server. There's some event that comes in and the web server has to respond in some way. And one of the best ways to respond to events, at least for a lot of activities, is with rule languages. Rule languages are a bunch of different kinds. There are constraint languages, there are deductive languages, and there are what are called responsive rule languages, which are the ones that are most appropriate for what we want to try and do. And rules in those languages basically look like this. When an event occurs, if a condition is true, then take some action. They're called ECA rules because we have events, conditions, and actions. Now remember, what we're trying to do is span multiple silos. So we need an architecture, not just a notation. Here's a generalization of an architecture that can make this work. We need some kind of active client. That is, we need something that understands that it's sending events to this rule language and accepting those responses. Now in browsers, that's pretty easy because browsers already know how to send events, and if we can just transfer those up to the rule language, we're ahead. And they already know how to execute JavaScript, so that's a win. Other devices like email clients, for example, need a little bit more help. We also need data. Fortunately, there's a lot of people building a lot of APIs, and that problem is not necessarily taken care of, but there's a lot of smart people working on that problem. And I'm proposing we also need a rules engine. Let me show you how this generalized architecture maps to what we've built. I don't want this to feel like an advertisement, but I am going to talk about what we've built because I think it's an example of doing this. I would welcome other people who've done similar things I'd love to hear about it. So in the Kynetx architecture, what happens is there is some user with their client. And let's presume, for example, that they go out to Amazon. And while they're out at Amazon, their browser extension says, oh, I have a rule set that's appropriate for Amazon that this user has installed. So I'm going to make a call out to the Kynetx network service, raise an event, essentially, is what's going on. There'll be some response, which then gets fed into the DOM and makes some change. In this case, it's placing a little notification there that this book is available in the local library. Now, in this example, we're using the web. And in particular, we're using a certain kind of event called page view, but there are also other events that we might use, submit, click, etc. When a user clicks on this, that might raise a different event, which does something else. But we can generalize this past the web, as I said. What we can do is think about replacing that browser extension with more generalized endpoints, at least a notion of generalized endpoints. And then we could think about, instead of using a web browser, we could be using a mail client, for example. And we could have a number of events for mail. Mail received, mail sent, mail refiled, etc. And it doesn't have to be just web and mail, obviously. We could do RSS, we could do any generalized webhook, we could use XMPP and Jabber, those kinds of things. Those are all systems that can raise events. And a programming language then can be built to respond to those events. The Kynetx network service is essentially a big event loop in the cloud. That's what it's doing. It's just sitting there waiting for events and responding to those events. Now, how do you program it? Well, you program it using a rule language, which we call a Kynetx rule language. It's a domain-specific language that's designed specifically for handling events that happen on the internet and taking action. It's browser and device independent, and it's optimized for events. That's what it's built for. Now, the obvious question that every developer asks when you propose a new programming language is why? And this morning, Douglas Crockford said languages promote creative laziness, so that's one reason why you want to have a language. But then you might say, okay, yeah, but why a new language, right? Why not just use something that already exists? Well, part of the reason is because we want to build expressions in the language that are specific to this particular kind of problem. That's why a domain-specific language helps. We can, instead of just using libraries and tying them together, we can create idioms which are meaningful in this particular domain. One of the things I've found throughout my career is that every time I build a web interface, or actually any kind of interface, web or not, people pretty much use it exactly how I expect them to. Maybe not as well, but they never surprise me. Every time I've built a language, people shock me with what they do with it. They come in and show me things, and I go, how did you do that? I said, well, I used your language. Really? I didn't know it could do that. And that's because languages are naturally, they're like tinker toy sets, right? People see all the pieces, and they put them together in designs and patterns that the language designer never thought of.